a class on pattern formation, gotten mostly out of these two books. This book, Rebecca Hoyle, and then there's demonstrations from the same sources, those from before. Mike Cross, professor of physics, said I always meant to write the demonstrations over again, but didn't get around to it. Okay, so I've alluded a little bit to the central problem of pattern formation before. We have put in eigenvectors, or when we've looked at linear stability, we've written something of the form, e to the I k dot x. Okay, and so these are plane waves, and their isocontours, say, can look like this. Would be this k vector, and then you could have another k, the same magnitude, that would look like this, and all of the equations and the things that we have gotten end up specifying merely, if that, a scalar k. So you could say what direction is chosen, but of course that, in the context we've been discussing, doesn't make any sense. If we're talking about a linear, homogeneous, infinite plane, there's no reason to have any particular direction. So you might think there's a superposition, and that would be true. The usual picture, if you just had in 1D, if you were just doing pitchfork bifurcation, dot equals mu x minus x cubed, you know what happens. You first start off with linear, for x small, you would have x of t equals e to the mu t x of 0 for a little while, until this term kicks in and your time series would look like this. We saw some of this for the cylinder weight. It would look exponential, and eventually this cubic term would cause it to saturate and stop, and you would have the solution x equals plus or minus square root of mu, and that would be the end of it. You didn't have any, you would choose between plus and minus square root of mu. But here you have an infinite amount of choice. You have all these possible things. Their amplitude is going to grow, and you don't know, as far as linearly goes, and you don't know where you're going to go in the end. You don't know you don't know what combinations are going to be allowed, and that's what the science mathematics of pattern formation is meant to answer. And it's not yet a complete field. It's again like with dynamic system, it's an approach. All the questions aren't answered, as I guess is the case in many fields. Here I've written Q instead of K. And everything we did with linear instability was dependent on the magnitude of Q. Now, the nonlinear terms that are going to, the relative sizes of the different UQs will give you the pattern. And we're not ready to just, now the mathematics is not ready to just tell you what the pattern is based on what the equations are. It's still a growing field. So let's give examples of all of this. Let's start with the Swift-Hohenberg equation, which is a simplification of the stability of a trivial state to eigenvectors e to the iq dot x, with a growth rate sigma of q, where q is not a vector, q is a scalar. Sigma depends on q squared. Why is that? Because, of course, only the magnitude of q matters, hence, and the only way to do that analytically is to depend on q squared. You don't, plus and minus q are the same. It's an even function. Even functions are power series q squared. And we suppose that there's a critical value qc, and q is positive for near qc and negative far away from qc. And so the lowest order function that does that is a coordinate function like this. You have a maximum at qc, and you're even. You have a maximum, but you're even. Otherwise, you could just make your maximum here, and it could just be right? So to be even and to have a maximum, it's got to be quartic, and this is the general form. Okay? Now we can derive the Swift-Hohenberg equation by transforming all of these symbols into their corresponding differential operators. Sigma usually goes, why do we get a sigma? Well, it's from d by dt of e to the sigma t, so let's change sigma to dt. Q, that's from the Laplacian, e to the iq dot x. So let's put a Laplacian there. So here, or rather minus, Laplacian gives you minus q squared. So right away, here we have the Swift-Hohenberg equation, or rather the beginning of it. Here, this was the equation of the argument. Here's Swift-Hohenberg equation. And we put in a cubic term as the simplest nonlinearity.
So
Yes.
QC was a scalar?
It's a scalar. Yeah. And QC will tell you that you have a pattern that, it's a pattern that looks like this, and not one that looks, say, like this, or that looks like this, in the convection rules. Or maybe this is what you look like. Maybe your physics tells you you do look like that, in which that case, that would be
You
QC.
standing in front of the diagram, sorry.
Anyway, Q, 2 pi over Q is the wavelength that the pattern wants to form. And this equation was derived in 1977 as, again, simple model problem. So the Swift-Hohenberg equation can in fact do remarkable things. That's really it. It's right here. And you see how it was gotten just by taking sigma with the properties you wanted and then adding the u cubed term. Let us look at some of the patterns that can be obtained. I hope I have that set up right. Safari. There we go. Let's start again. Oh, I just started. It was working, and then. Oh, now I have to stop it again. Yeah, all right, stop it there. Safari quit. Safari start. Go to history. Run. Okay, this is merely a numerical simulation of the Swift-Hohenberg equation from random initial conditions. And here's what it's doing. Now notice some of the things it's doing. It has a little problem here, you can see, kind of defect. It's going to eventually form stripes. So straighten itself out. Now let us look at this from the Fourier point of view. Do a 2D Fourier transform of this. Let's look at it. I thought of, okay, this is random data. Let me look at the evolution in Fourier space. Okay, that's what stripes look like. This is this is plus k and minus k. And so the stripes are going to look like this. Can we do this in the same real time? Stop. Stop. Can we do it? Yes. No. I think this used to be possible. Oh well. It's, okay. Not a number. No, wasn't it? Can I stop it? No. Can I reset it? No. Okay. Well, let's go to another demonstration. There. Okay. Okay, I'm going to run this one, and the difference between the one that you saw and the one that you're going to see now is this G1 thing. Before the G1 was 0, now the G1 is 1. Let's start it. And here formed hexagons. It just did that, spontaneous. Hexagons were not, no hexagons were harmed in the course of this filming, no hexagons were inserted in the course of this filming. It spontaneously formed hexagons. Okay, let's stop this and see if we can look at the FFT. Come on, can you do that? Yes, okay, so the FFT, remember that the Fourier transform of a hexagonal lattice is a hexagonal, and here it is, with a constant term as well. Continue it, I think. Can we? Yeah, from here, perfect hexagons. If we start, okay, let's reset. We start from the random data. This is with not FFT, and now, yeah, this is FFT data. Okay, and you see it very quickly collapses down. This is the circle Q equal QC. But it's not hexagonal yet. Let's see if we can see what it looks like. Stop. Now we're going to try and look at it in the physical space, this imperfect, it all has the right wave number, but it's not on a hexagonal lattice. And you see it's kind of imperfect. You see all those little problems it has? That part takes a long time. Stop. Show the FFT. Start. And it's still evolving. You can see it's evolving in time, and it's trying to get itself settled into hexagons. But that part's very slow. Stop. Look in the physical space. Start. You can see it kind of struggling. It's getting itself. Come on. This one has only 5 around it. You see it has a problem. It'll fix itself up, but it will take a while. Okay. And now we can go back to the stripes and see this now that I have a little more control. Yeah, this one has this term G1 of 0. Let's start it again. Okay, so it has problems. You see it has this little problem, but they quickly sort themselves out. Stop. Start. Here you see that's what the stripes should look like this, and that's what they look like, right? That's their orientation. Let's look at the whole evolution in Fourier space. Reset. Start. There. It quickly goes to being on the stroke. It's not quite right yet. Stop. Let's see what that looks like. You see it's mostly, you'll see this is the wave vector, and the stripes are going to be perpendicular to the wave vector. The wave vector tells you the direction in which there's variation. So it should look like stripes like this, but it's not quite right. And let's see what that looks like. You see? And that's the not quite rightness. It's going to fix itself up, but that's going to take a while. Okay, so the point is to understand a little bit these principles that led to this this formation. Okay, and that G1 that we're talking about is here. Recall that when we did the Swift-Hohenberg equation, I mean, this is what it looks like. We had a mu here. We had +1 here, a Laplacian. What we had was plus and then minus Laplacian squared. You know what we had? Anyway, it was this term, but with the QC here. Your QC is 1. We had a cubic term. We said that was the simplest saturating term. But here's a quadratic term. Here's a quadratic term, and that's the G1 that I said is 0 here and was not present for the hexagons. And you'll understand that very shortly, the presence of this quadratic term or not. Okay? So now we go back to this. And so that's what's being shown here. We easily get stripes and hexagons. And we'll see that we can also get quasicrystals. We mentioned this a little bit yesterday. And we get and we'll talk about various instabilities, all from the Swift-Hohenberg equation. Okay, let's start with the simplest thing, stripes and rolls. here's the Swift-Hohenberg equation. We're only going to be 1D for the moment. We're used to this by now. This is kind of like, this is adjusting mu a little bit, right? We're going to increase mu, and eventually we'll get steady states. Here is, excuse me, we have steady bifurcations when, excuse me, we always have the solution u equals 0, and u equals 0 loses stability, we're used to that by now, at mu equals this square here, excuse me, at mu, mu minus qc squared plus q squared equals 0, successive bifurcations, and the curve of that as a function of q looks like this. It's a quartic curve. Okay. And there are bifurcations at the values that are permitted by the box size. We have q equal a multiple of 2 pi over L, and that's what's being shown here. Multiples of 2 pi over L are shown here. And as you increase mu, you get more and more permitted branches, and they're shown here. This is the u values. This is u squared equals mu minus qc squared plus q minus q squared squared. These are the curves, these quadratic curves here. As you increase mu, you get more and more of these, because more and more of the permitted values of q are multiples of 2 pi over L, because that's what fits in the box. And more of these are permitted in the box, so you get more and more branches. Okay? And this is just that data in tabular form. Yeah, I guess there's no point in, you've seen it in the picture. You see that as you're increasing mu, you get more and more branches. And now, all of these branches are circle pitchforks. In what sense are they circle pitchforks? You know, that Tom Friday, I drew them many times. I drew something that was stable here, and then it became unstable, and the new solutions looked like this. And we said this was not a Hopf bifurcation. You don't go around here. You stay wherever you are. It's just a choice of phase. You have a circles with. So what does that mean in this circumstance? Well, we just drew these convection cells here. If we were in a periodic box, just draw many of these here. If we were in a periodic box, then what we would say is that this is one solution. Say, let's call that this solution. Then this is one solution. Let's call that this solution. This is one solution. That's this solution. So a choice of phase. Okay, and you can see, of course, why they have all the same physical properties, and it doesn't matter what your choice is of 0 in trigonometric functions. So each is a circle pitchfork. And now there are two limiting cases. Suppose your box is so big, your periodicity box is very, very big, then it doesn't really matter to this. It can allow many possibilities for the size. Changing from 20 to 19, no, it's going to change to an even number. 20 to 18 rolls doesn't really change the size of it very much. It might be kind of happy to do either one. There's one that it'll prefer, but the other one isn't far behind. Or you can have a small box. If your box is this size here, about the size of a critical wavelength, then you can see it's not going to be very happy to do anything other than this. To do something other than this, it would have to have twice as many. They would be much thinner. They would be more like that. So those are two very different cases. One in which we're basically only the first one is going to happen, and the other limiting case in which sometimes you don't even take the discretization into account and you take Q to be a continuous variable. Okay, so that's kind of the end of 1D. Let's go on to 2D. Let's discuss square patterns. Remember I told you about Faraday instability produces either square or hexagonal patterns. We're going to discuss both. So let us look, that we're now in the case, in this case, we're only considering the first bifurcation, only the first wave. So we write our expansion like e to the I, basically we have a wave number of 1 because we've taken our units that way. We've taken our units such that wave number of 1, that means critical wave length is 2 pi. Yeah, so we've taken a box of size 2 pi. So 2 pi in terms of. Okay, yes, that's what's written here. Good. Okay, so when I write e to the I plus or minus I x1 and e to the I x2, I am not talking about two different lengths. I'm talking about this direction and that direction. I could have called them e to the ix and e to the iy, but I'm preparing for the hexagons where I'm going to have a third one. Okay, so consider 1 is this direction and 2 is that direction. And so you may have gotten used to this or not from what we did on Friday. We're going to write our field as a combination of time-dependent amplitudes, Z1 and Z2, and their complex conjugates, times the eigenvectors. And then doing that, we'll see what we can learn by doing this. We will see what kind of equations we get for Z1 and Z2. This part you just accept. We have taken the eigenvectors that are plane waves in the x direction, plane waves in the y direction, and we're just going to write this down and see where we can go. We're putting that's effectively we're putting our problem on a square lattice, and the symmetries, if you want to be formal about symmetries of the square lattice, are the rotations. You did this again in Friday's class. The rotations by pi over 2, rotation by a quarter, 1/2, 3/4, 1, and reflection. In addition, we allow for translations in any direction. We really have a lattice, not just a square. So let's see, when we put in these, this is what we did Friday a lot, when we put in these symmetries, let us see what consequence there is for these z's. We're going to put the symmetries onto the u's, and then we're going to see what that leads to for the z's. Okay? So let us rotate something that's a function of x1, x2, and t. Well, that is like, I'm sure to get the sign wrong, but I can try. At least it will be entertaining. If I have something that's like this, x1 and x2, and I rotate it, supposing I have a little patch over here, and I'm going to rotate the whole thing. I'm sure, I don't even know, why am I trying this? I'm sure this is going to, it's going to fail. Okay, but I'm going to rotate this, and now this is going to be x1, and this is going to be x2, and my patch, my patch that used to live in the x1 direction now lives in the new x2 direction, but at minus where it was. Does that correspond to what that is? Sort of?
Yes.
Yeah, okay, good. All right. So I repeat the definitions of symmetry operators. We have turned this function u into by operating with this rotation, we've turned it into a new function. That's the which is related to the old function in this way. This is an operation. Okay, we're not saying anything about any properties. We're saying this is instructions for how to turn a u into a rotated u. Okay, now we're going to write the expression here for this. So we're going to, the first argument is going to be x2 instead. We're going to have z1 x2 because that's what this says here. And the second argument here, the one that used to be, the red one that used to be x2 is going to be minus x1. And then we have the complex conjugates. Okay. And what we want is for, okay, so we've done that. And then we see that we can accomplish this operation on the u's by accomplishing a certain operation on the z's. How do we do that? Well, the thing that multiplies e to the ix1 is now z2. Excuse me, no, it's not, excuse me, so, no. It's now z2 bar. Right? So that motivates the idea that what we're going to do, if we instead of operating on the u's, we operate on the z's, we're turning this first place in the z's is what multiplies e to the I x1, and what multiplies e to the I x1 is z2 bar. So that tells us that our operation, the equivalent of this operation on the u's, but carried out on the z's, is to have z2 bar over here. And similarly, then we have z1 here, because that is the thing that multiplies, z1 is now the thing that multiplies e to the I x2. If we wanted to do a reflection on u, well, a reflection in the horizontal direction, we would just change x to minus x, so that would be that we'd change z1 to z1 bar. So that's what's being done here. Translation by p in x1 and x2, well, that would be like moving x1. We would take x1 to x1 plus p1. And so we see that that would be the same as multiplying z1 by e to the ip1. And so 2 and p2.
Sorry, what is translation?
Translation,
I mean, again,
here.
like rotation and reflection, I can imagine like how it works.
Right, okay, I see. This one, yeah, because it's true we didn't do anything like that before. You have a solution here, and you're just going to move it over to here, just like what we did there. Moving it over,
Oh,
that's all. Or, that's it, that's P1, and then P2 would be, you would move it over, I should have made a square like this. I would move it over a little bit this way.
thanks.
Okay. And we want our governing equations to be, to not care about any of those things, obviously, right? We don't. Okay, that's what symmetry means. So we want our governing equations to be equivariant under these things, meaning take what we just did, well, we'll see. We seek terms which commute with all of these operations. The most, okay, we're used to this. To commute with kappa, we'll want the coefficients to be real. Let's do that. Let's look at that over here. We're going to, since we're going to change z, okay, well, this we did before. We did it, just think, possibly people weren't here before. We had polynomials that were f m z to the m. When we did kappa, okay, this was f. When we did kappa on f, we turned it into its complex conjugate. But when we did when we did first kappa on z, we turned it into its complex conjugate before doing, excuse me, we did z here. And then when we did, so here if we did f on kappa of z, then that would mean taking the, that would mean taking, using complex conjugate wherever we had that, right? A kappa of z gives z bar here, and then we would make that Taylor series. Whereas here, if we did, I'm sorry, I said, this is not what I meant.